Hello, this is the Section 9.5 notes for Statistics Honors. If you recall, prior to the break, we talked about confidence intervals and a little bit of hypothesis testing. And when we did confidence intervals, we started with Z intervals, which occurred when the population standard deviation was known. Well, then we had to move on to T intervals whenever the population standard deviation was unknown. So we're going to do the same thing with hypothesis testing. We talked about a one mean z-test prior to the break. This was also when the population standard deviation was known. So now we have to talk about when sigma is unknown. If you look at the setup for a one mean z-test, you'll see that the assumptions are pretty much similar, except the obvious unknown situation with sigma. But remember, we do need a simple random sample and we need a normal population or a large sample when n is greater than or equal to 30. Null hypotheses and alternative hypotheses are all going to be set up the same way, so not a big deal in terms of any changes in that department, and alpha is not going to change either. Just remember that when we're talking about this stuff, that the test statistic is going to be a little different, but that's because it's t instead of z. So remember, z in this setup was actually z equals x bar minus mu sigma over root n. So now we're going to have to make the adjustment to the t-test statistic, where s is going to replace sigma, and of course t and z are going to be different. Part of the situation with this, once again, is when you're doing these problems on an exam situation, they're not going to tell you which one to use in terms of which test, so you're always going to have to be on the lookout for the standard deviation, whether the population standard deviation is known or unknown. So we'll keep that in mind as we're going through the problems. Okay, so if you recall, when we did the z-test, we talked about two approaches, the critical value approach and the p-value approach. We're going to start with the critical value approach for the t-test because you have to know both approaches for the test. So we'll start there. You'll see that the setup is very similar, except now we're going to be in a different table because for a z-test, you're talking about the typical Table 2 area under standard curve with all the areas, and for a t-test, we're now talking about degrees of freedom coming into play. So that's what we're going to have to concentrate on when we go through all this process. Okay, so just as a reminder, when we're using the critical value approach, for z-test, we used z sub alpha whenever we're using a one-tailed test, and we used z sub alpha over 2 whenever we're using a two-tailed test. So we're going to do the same thing when we're dealing with t-tests. So t sub alpha for one-tailed, t sub alpha over 2 for two-tailed. Remember, these values are the key values that form the rejection regions when it comes to a t-test. So let's just do a little bit of practice to make sure that you're comfy with this stuff. So looking at number 1 here, it says, let's say you have a left-tailed test with n equals 18 and you are at alpha 0.05. Suppose the test statistic is negative 1.25. Okay, well, first things first, we want to concentrate on these two values. On a left-tailed test of n is equals to 18, we know that from previous studies that degrees of freedom is equal to n minus 1. So therefore, we have 18 minus 1, which is equal to 17. Now we have a degrees of freedom of 17. We also have a one-tailed test. So the important critical values are going to be placed at, or the critical value is going to be placed at negative t sub alpha. So that would be, in our case, negative t sub 0.05. So our goal in these problems is to find the critical value that is placed at negative t sub 0.05 at degrees of freedom 17. So we're going to go over the t-table, and we're going to find degrees of freedom 17, and we're going to find t sub 0.05, doesn't matter if it's negative, and we're going to locate 1.740 as our key value. So we're going to go over to the negative side, and we're going to have negative t sub 0.05 is negative 1.740. Now, remember, the t-table only displays positive values, but because of the symmetry of the table, we know both sides are going to be the same. So this value is going to be marked somewhere in this location as negative 1.740. So if you recall from the critical value approach for z-tests, we always reject h0, or the null hypothesis, in the tail, and we do not reject h0 anywhere else. So the only thing left to do is determine from our test statistic right here, which is provided, we want to decide in this scenario, would we accept or reject h0? So where does it fall? Well, it appears that this falls somewhere around right here at t equals negative 1.25. You can clearly see that in this scenario, that negative 1.25, our test statistic, is in the acceptance region, or the region where we do not reject h0. So therefore, we make a conclusion that we do not reject h0. Okay, so hopefully you're sort of remembering this from when we did critical values for z-tests. It's just now we're in a different table when we're looking up the critical values. Okay, let's move on. So let's say we have a right-tailed test. So we have n is 99, alpha is 0.10. We can deal with the test statistic later because that's what we use for our decision making. So let's set this up. So according to this, the degrees of freedom is going to be 1 less than n, which is going to be 98. So in this scenario, we would normally go, okay, we got 98 degrees of freedom. We have t sub positive alpha in a, yes, that should be, I probably did the same thing in the other one. That should be alpha, and yes, this should also be alpha. Right. Okay, so as we go through it, we have t sub alpha is going to be equal to t sub 0.10 positive in a right tail test. Makes sense because we're on the right side of the curve. So in this scenario, we would go to our t-table and we would try to find our important values. Let's get rid of those for a second. So we would go to 98 and we would clearly see that we have an issue here. So just like we did when we talked about t intervals and we had to choose important values for those of t, we're going to do the same here. Remember, you always round down to the nearest degrees of freedom. So we're going to be picking 95 for our degrees of freedom. And remember, we are looking at t sub 0.10. So that is here. So if we look at that, it looks like we're going to get for our critical value 1.291. So we go over to our right side and we're going to have t sub 0.10 is 1.291. This is going to form our split between our reject h0 and our do not reject h0. So the only thing left to do is to make our ultimate decision in this scenario. And by the way, if you want to make a note here, use df equals 95 for your notes. There you go. So in this scenario, it looks like our test statistic is 1.82. So 1.82 looks like it's going to fall somewhere over here to the right of our test statistic, which clearly falls in our rejection region. So we can clearly make our decision of reject h0. Okay, so in these scenarios, just remember with one-tailed tests, we're doing either negative t sub alpha or positive t sub alpha in this scenario. So what happens when we move to a two-tailed test? So recall that for a two-tailed test, the degrees of freedom does not change, so we're still managing with these guys. So we are going to have degrees of freedom equal to 1 less than 68, which is 67. But the big change in a two-tailed test is that we're using now positive and negative t sub alpha over 2. Therefore, if we look at alpha being 0.01, we're actually looking at positive and negative t sub 0.005. Okay, these are going to be our critical values. So remember two-tailed tests, we need two values, hence two tails. So we go over and we're looking at T sub 0.005 at 67 degrees of freedom. So let's get rid of this so we have no confusion. Okay, so we're back to here. We're looking at 67 and T sub 0.005. So if you look really closely and you make the connection this way and this way, we're going to find that 2.651 will be our critical value. So we're going to go over to our chart here. We're going to have negative 2.651 and positive 2.651. These are going to be our barriers for our values. So this is negative T sub 0.005. This is positive T sub 0.05. Okay, so therefore remember, two tails this time, but still we always reject in the tail. Reject H naught. And then do not reject H naught. Okay, so now we have two areas where we could reject. So what do? Again, we find our value of our test statistic, which looks like it's going to fall around right here at 2.50. So clearly, we have a value that is inside the non-rejection region. So we stick to that and say that we do not reject H naught. All right, so let's check out the p-value approach for t-tests. This can be a little bit trickier. The z-table is very easy to find areas for, but in reality, in t-table, we have a different situation. If you're looking at just the situation here, remember t sub alpha has an area of alpha above it. So essentially, there's an area in alpha in the tail. But remember, p-values are tail areas. So when we're looking at a t-table, believe it or not, the areas are actually in the subscripts of our values at the top. These areas are p-values depending on alpha over 2. Remember, we're going to be dealing with that, so we'll talk about that a little bit more later, but let's just see how this works in the actual problem. So I'm doing redoing problems 1 through 3, but this time using the p-value approach. I'm doing this because we should get a result of do not reject, reject, and do not reject as we go through this. So let's see how it works. So remember, when n was 18, we were dealing with df is equal to 17. Okay, I imported the table in here to make life a little bit easier for us when we're doing the notes. So, what is the goal? How do you figure out what a p-value is in a t-test? Well, in this scenario, remember that when you're doing this method, you can't find the actual p-value. You can only find the interval in which the p-value falls. That will be good enough to make a decision, by the way, but I'll show you what that means in a second. The goal is we need to take our test statistic, negative 1.25. Remember, the negative does not matter because all values in the t-table are positive. We need to look at that and say, look at positive 1.25 and find out where that falls in the row of degrees of freedom is 17. Well, if you look at the row right here, it looks like all the values are increasing from left to right. So if we were to locate where 1.25 goes, it would be about right here in our table. It would be less than 1.333. So we use that knowledge to make an idea of what the actual p-value would be. Well, this is the important part. So this right here means that at 1.333, the p-value would actually be 0.10. Therefore, if you look at the subscripts of the t-values, it appears that the t subscript to the left of t.10 would mean a greater p-value. Why is that? If you look to the right of t.10, it's a lower p-value of 0.05, and then even lower as you go to the right. So for this scenario, we would essentially say that the p-value, the only thing we know for sure is that it is greater than 0.10. Why does this help us? Because our alpha in this problem is 0.05. For any p-value greater than 0.01, we clearly are going to do not reject H naught. Okay, so this can be a little tricky because you have t-values increasing and you have areas that are decreasing from left to right, so it'd be a little crazy. So let's do a couple more just to make sure this sort of settles in. So in a right-tailed test, remember, degrees of freedom here for 99 was 98, but what did we have to use? We had to use 95, because recall in the table, as you see right here, it goes from 90 to 95 to 100, so we're here. Okay, so remember, we're in a right-tailed test, so we're just using single t sub alpha. So we go to our test statistic over here, and we go, it's positive 1.82. So again, we're going to look at these row of values, and we're going to see where 1.82 falls. Well, if you look closely, it appears that it falls somewhere in between 1.661 and 1.985. So what does that help us with? Well, that means that we are somewhere between the area 0.025 and 0.05 in terms of tail area, which in turns is our p-value. So therefore, we can say that in a compound inequality, that 0.025 is less than p, which is less than 0.05. In other words, p is somewhere in the interval between 0.025 and 0.05. Why is this important? Because if you look at alpha right now, alpha is 0.10. So no matter what p-value you pick in this interval right here, we know that that is going to be less than 0.10. Therefore, we can reject H naught. Okay, so this is for one-tailed tests. So again, a little confusing. We're going to have a little bit easier way to do that soon with the calculator, but for now, that is the idea. So what's different about a two-tailed test? Believe it or not, in the beginning, nothing. All the change is going to happen at the end when we determine what the p-values are going to be. So again, returning to the previous problem we had with n is 68, we have df is 67, so we are dealing with this guy right here. So we're looking at all these values, and we're trying to determine where the test statistic 2.50 falls in this medium. Okay, so if this is true, we look on here and we go, wow, it's actually much higher. It looks like it's going to be somewhere right here between 2.383 and 2.651. Okay, so here's the deal. Normally, if this was a one-tailed test, we would say that the p-value falls between these two values. But here's the problem. These values are actually the area in one tail. We want the area in also the shadow tail on the other side, which means we have to multiply both of these p-values by 2 in order to find the p-value. So we're actually, it's a little bit weird, but we're basically looking for 2 times 0.105 would be the p-value falling between that and 2.01. So instead of just between a single 0.005 and a 0.01, we need the other tail to come into play for the p-value, so it's going to be between double these. So if we do the math, we're going to get the p-values actually between 0.01 and 0.02 in this setting. Therefore, if we look at alpha 0.01, we go, well, no matter what p-value you fall in the setting, it's going to be bigger than 0.01, which means we do not reject H naught. All right, so yes, the process of that can be a little tricky, I admit, but we do have a nice alternative, which is, normally I'm perfectly fine with you using in terms of on exams and such. So if you, on your calculator, you have seen before that when you go to second, let's use a different color here. When you go to second distribution, right here, you end up with a screen that basically has, you've already seen normal CDF on there. You're going to be choosing TCDF for this case. Okay, so remember, most of you will have a nice, easy input device when you go in there for TCDF. Others will have to type the exact value in, but the key is that if you actually have, a T graph just like this, and you have 1.82 as your value, then for, in this case, number 2, so just as a reminder, let's go back to number 2. So we had the test statistic was 182, and you want to find how much area is to the right of 1.82. That'll help us find our value. So if we plug that in, remember that you're going to do lower bound, upper bound degrees of freedom. So our degrees of freedom in that problem was 98, which is right here. Remember that we use this as the biggest number, as large a number as possible, 1E99, and 1.82 is the minimum value. Now, if you put this into the calculator, you're actually going to get 0.0359 as the actual p-value. So again, if you remember this, if you go back, this was number 5 was actually the problem right here. Number 5 was the problem that mimicked number 2. So remember, we actually concluded that the p-value is between 0.025 and 0.05. Well, now we know what it exactly is, 0.0359 using our TCDF. So you already know how to use normal CDF, so this shouldn't be a big jump, but that's basically what you'll be doing in terms of trying to find p-value for a test statistic of t. All right, so let's take a look at some examples using t-tests right off the bat here. The goal is we're going to be looking at both critical value and p-value methods. We wouldn't normally do that all at the same time, but we're going to do it just to make sure everything is understood with the concept. So it says an insurance agent says the mean cost of insuring a 2-year-old sedan is less than $1,200. A random sample of 7 similar insurance quotes has a mean cost of $1,175 and a standard deviation of 55. Is there enough evidence to support the agent's claim to alpha 0.10? Assume that the distribution is normally distributed. So remember, t-tests require three checks that you have to make. Remember that the sample must be random. It looks like we're good there. We must have a normal distribution. It appears that we do have that normal distribution. Note, it does happen to be that there are only a sample of 7 for this, 7 quotes. So we really do need this to be an actual normal distribution in order to make this work. Okay, so lastly, we want to verify that this population standard deviation is either known or unknown. If you read the statement of the random sample, which is right here, it implies that the actual standard deviation is coming from the sample. Therefore, we would look at this and we would say the standard deviation is clearly going to be S. So as a result, we can say that we are definitely going to be working with a t-test. So we want to make a null and alternative hypothesis, so we start with that. Okay, remember the null is a statement of equality. It looks like our mu is right here. So we have $1,200. The alternative keyword is here, less than. So we're doing less than $1,200. Okay, and they do mention that alpha is 0.10, just FYI. That is a formal step, but something that we will manage later. So for the t-test statistic, we will be saying t is equal to x bar minus mu s over root n. We just have to fill in the numbers. So the mean cost of the quotes was $1,175. We need to subtract 1,200 and divide by s divided by root n. Okay, in this case, we do a little bit of mathematics, little calculations. We're going to get negative 1.20. So that is going to be our test statistic. All right, so once we have the test statistic, we have basically 2 different methods. So we have critical value and p-value method. So again, we wouldn't actually use both methods. We would just use one, but why not for practice purposes? Sort of take a look at both of them and make sure all is good with using them. So if you recall, with any left-tailed tests, so clearly we have a left-tailed test right here, we are going to be using negative t sub alpha as our critical value. So here that would be negative t sub 0.10. Clearly, though, we have to know the degrees of freedom. So the degrees of freedom is going to be 6. How do we know that? Because remember, the sample size is 7, and we subtract 1 in order to get the degrees of freedom. So in this standpoint, we basically know now that we have that as our setup. So what do? We need to look that up. So we're going to look up t sub 0.10, which is right here. We're going to look up 6 degrees of freedom, which means it looks like we're at 1.440 as our number. So moving on back to our notes. Negative 1.440. How do we know? Do we make it negative? Because we're using negative t sub alpha. Okay, so what would we do? We would plot this value somewhere on our graph. Must be to the left of the mean. So we have a little barrier there. We reject in the tail and do not reject everywhere else. All right, so how do we, the last piece of the puzzle is we have to take our test statistic, negative 1.20, and we have to place it on the graph. So if we place it on the graph, we're going to get this as our value. And this is officially looking like it'll be in the do not reject region. So what would be the conclusion? So remember our little conclusion summary here. We would do not reject H naught, which means it does not provide sufficient evidence. And then we would just reword the alternative hypothesis that the mean cost is less than $1,200. Okay, so why did I include the p-value stuff here? Well, just as a nice little practice so that everything is good. So why don't we take a look at that? So what if we wanted to compute the p-value? I gave you 2 methods. One is finding the interval and one is finding the actual value. So what if we were to find the interval? So remember, we are again at t sub 0.10 at 6 degrees of freedom. Our test statistic is 1.20. So we would basically go to 6 degrees of freedom, which is right here, and we would look at all of these values here and look where 1.20 falls. That looks like it would be all the way up here. So that means our p-value would have to be larger than 0.10. So we go over here and we say, all right, so our interval would have been p is greater than 0.10. Okay, well, if it's greater than 0.10, we look at our alpha value right here, and we say, clearly, if it's greater than alpha, then we would not reject H naught, which basically clarifies our decision. Okay, last thing, if we want to find the exact p-value, we would use the command tcdf to find the area to the left of our test statistic. So how would we do that? We would say, all right, well, if we're in the left tail, we would want the smallest number we can think of from our calculator. We would move to our test statistic, and then we would use our degrees of freedom. If we do that, we are going to get a p-value of approximately 0.1377 as our value, and clearly that is greater than 0.10 and leads us to not rejecting H naught. All right, so let's take a peek at problem number 8. Okay, so it says a researcher estimates that the average height of the buildings of 30 or more stories in a large city is greater than 500 feet. A random sample of 10 buildings is selected and the heights and heat are recorded. Assuming that the distribution is normal, is there sufficient evidence at 1% to support the researcher's claim? Okay, so the little things. We want this to be a random sample. We also want this to be normal, which is very important because there's only 10 buildings. Lastly, we want to make sure that the standard deviation is actually coming from the sample. But if you notice very clearly here, we actually only have a sample. So what does that all sort of mean for us? Well, if you're only given a sample and they don't give you the population standard deviation, which you can clearly see is not given in the problem, that means the only way to accomplish this problem is to plug this into the lists in your calculator. So yes, we're talking L1, right, in the calculator and lists, which you've done many times, and do a little 1var stats in order to find x bar and s. So if you do so, you will end up with an x bar of 606.5 and a sample standard deviation of 109.1. So if we have this, then we can then proceed with the problem as if we're doing a t-test, because the population standard deviation is officially unknown. So remember hypotheses. We know that mu is a state, or the null hypothesis is a statement of equality. So it looks like our key value of mu is 500 feet. And we have a very important keyword of greater, so we know that our alternative is greater than 500 feet. And it appears that alpha is 0.01 for this particular problem. Okay, so we have to move on to our test statistic and do our calculations. So remember, we're doing x bar 606.5 minus mu, our 500, divided by, we have our 109.1 divided by the square root of 10. Okay, calculation will give us 3.09 as our test statistic. Okay, so let's talk about our critical values. So what are we dealing with? We're dealing with a right-tailed test, clearly. So in a right-tailed test, we have positive t sub alpha, which means we want positive t sub. We're dealing with 1%, so 0.01. And we have at degrees of freedom equal to 10 minus 1, which is 9. So what do we do? Again, we can revisit our t-table, where we can find t sub 0.01 at 9 degrees of freedom. So we're here, here. So therefore, it looks like we have 2.821 as our value of importance, 2.821. So remember, this is the positive version, right? So positive 0.2821. So we can go into our curve up here, 2.821. Create our boundary on our right tail. We know in the tail we reject H0. And we know anywhere else we do not reject H0, DNR. Okay, so the only thing left to do is to take our test statistic, which we clearly see is 3.09, which is here, and we want to mark it somewhere on the graph. It looks like got about t equal to 3.09 over here. So that's clearly in the rejection region, so we are going to reject H0. So if we're looking at our main situation here, we're basically going to say, let's reject H0 for our conclusion, which means it does provide sufficient evidence. And then we want to reword our alternative hypothesis. So we're going to do that. All right, so what is our alternative hypothesis? Simply that the mean height of the buildings is greater than 500 feet. So we're going to rewrite that. Mean height of the buildings is greater than 500 feet. Alrighty, so just like before, let's take a peek at this p-value just so we can do a little bit of verifying about this rejection. So in order to find the p-value interval, we must look at our test statistic, which is 3.09, and see where it falls at degrees of freedom equal to what do we got here? 9. Okay, so degrees of freedom is 9, which is here. So we're looking at these values right here, and we're looking for where our 3.09 falls. So if we look at that very clearly, it looks like it's right here, which means that our p-value must be between these two values right here. So let's rewrite that. So we have 0.005 is less than p is less than 0.01. Okay, so worth noting, any p-value in that range is going to be rejected at our 1% alpha. So we verify that we are rejecting. So what if we want to know that exact value? Well, the key is that our p-value will be equal to TCDF. Okay, we're in the right tail this time, so we want to go from 3.09 to 1E99 with a degrees of freedom of 9, and that's going to give us approximately 0.0065, which is absolutely between this interval and leads to a rejection. Okay, for our last example, let's take a peek at number 9. It says a large university reports the mean totaled household salary for both parents of an entering class is $91,600. To see how this compares to his university, a president surveys 28 randomly selected families and finds that their average income is $88,500. If the standard deviation is 10,000, can the president conclude that his college is different than the other one? Assume that the distribution is normal and alpha is 0.05. Okay, worth noting here, I can already see there's a little bit of a missing word, so just you're going to add sample before standard deviation. I forgot to correct that before, so just put that in there before we get started. Okay, so right off the bat, remember, what are we looking for? We're looking for a random sample. We're also looking for this being normal, and worth noting, this is pretty close to 30, but it's still just 28. So in this scenario, the only thing we need is a sample standard deviation or the lack of a population standard deviation. So you can see why this sample that I added in here, which should have been there to begin with, is very important, because it would have been really difficult to be able to decipher between which standard deviation that was. So hence why it should be in there. Okay, so null and alternative hypothesis. Let's take a peek at that. Null is a statement of equality. It looks like we got a claim value of $91,600 over here. Okay, and that means the alternative is either going to be less than, greater than, or not equal to. So even though the X bar is provided right here as 88,500, there's nowhere in this problem where it says anything about less than or greater than. As a matter of fact, the key word is actually right here. It says different than. No specifics are made, which means that we must use a two-tailed test to cover ourselves in this scenario, and of course, alpha 0.05. Okay, so let's move it to our test statistic. So we're doing X bar, which is 88,500, minus 91,600, our mu, over our standard deviation is 10,000, divided by root 28. Doing this calculation will get you approximately negative 1.64. Okay, this is our test statistic, the similar process from what we were doing. So now we have to move on to see what kind of decision that we're going to make here. So critical value. Critical value. So in this scenario, we basically are looking at this and saying, for critical values for two-tailed tests, we do plus or minus t, remember, is alpha over 2. So that's going to change things a little bit. So now instead of t sub 0.05, we're doing plus or minus t sub 0.025, which is alpha divided by 2. So just to be clear, alpha divided by 2 is 0.05 divided by 2, which is going to give you 0.025. So remember, we're doing this at degrees of freedom equal to 27, which is 28 minus 1. So again, what would we do? We would look in the t-table, which you are very well known for doing so far. Everybody understands that. We're going to end up getting plus or minus 2.052 as our value, just to verify, we got 27 right here, right? And then at 0.025, we're going to get the important values that we need, which is going to be 2.052. All right. So from that, we can create our two critical values here and here. Remember, we reject in the tails. We do not reject H0 in the middle. So therefore, we can look at this and say, let's take our test statistic of negative 1.64, place it in the graph itself, negative 1.64. Clearly, it's going to be in the region for not rejecting or accepting the null is what it is. So we go down to our conclusion. We do not reject, which does not provide sufficient evidence. And basically, the alternative here is stating that the mean income for the household is not 91,600. So that's what we write. So the mean household salary is not, you could say is different than if you want, because that's what they said in the statement, but this is fine as well. Synonym is fine of that. And we get this as our value. Okay, so we made our decision. Again, we want to, let's use some p-value stuff just to make sure all is good. This is going to be a little trickier only because we now have a two-tailed test. So remember, the key is the degrees of freedom. So the degrees of freedom is 27. So we're looking for that line in the t-table. And we need to place negative 1.64. So we go to the t-table. We go to our 27, and we're placing 1.64. So that is actually going to put us right here between these two values. Okay, so then we go up to here and we go, these are the two values of alpha. Or of our values that we need. The problem is that in our standpoint, these values are only one tail, which means we need twice these values in order to write this on here. So what is the interval? We need 2 times 0.05 for one end, which is the one value that was in there, and we need 2 times 0.10. So we're going to end up with 0.10 is less than p is less than 0.20. So just to clear, so if we look at the t-table, you can see right here our values are 0.05 and 0.10, but we need 2 times those values over here. So this is where our interval is. Now note, both those values are bigger than alpha 0.05. Therefore, this verifies that we do not reject the null. But what if we want the exact value? Well, this is also a little different. So in order to find the exact value, we need to use TCDF, but remember TCDF is only going to give us the area in one tail, so we have to multiply the TCDF value by 2, so it's going to be 2 times the TCDF of, let's start, since we have a negative value of the test statistic, let's start on the left side and go to that value at degrees of freedom equal to 27. If we do so, with it times 2, we're going to get 0.1126. So clearly that number is between our interval and checks out with exactly what we need. So we have our do not reject H0 conclusion.